The finite element method solves boundary value problems in structural engineering. An example of a boundary value problem is given by a simply supported beam. This beam has a load Q applied to it. This load can be a uniformly distributed load as well as a concentrated load. And it has properties D and geometry L. The boundaries here are illustrated by the supports. And this is why we call it a boundary value problem. The problem is described by an ordinary differential equation. And for this particular type of problem, the ordinary differential equation is written as d equal to the second derivative of y with respect to x plus q equal to 0. This is a standard ordinary differential equation used to describe bending problems. In this case, the coordinates x and y represent the distance along the beam, which is x, and y is the deflection. In this type of problem, we seek to solve for y. In some cases, it's possible to solve for y analytically. However, in general, this is not easy to do. So instead, there are numerous methods that are available. In this online video tutorial, we will focus on the method of weighted residuals. In the method of weighted residuals, we take a function y equal to h of x, and this is used to transform our original differential equation, noted by 1, into the following form: d times by d2h of x divided by dx squared plus q is equal to r of x, where r of x is the residual. Importantly, this expression Rx is not equal to 0 because it is an approximation. This is equation 2. The next step in this method is to introduce a not yet specified weighting function, w of x. This function is then used to form the following integral expression. We integrate from 0 to L. We have our weighting function, wi of x, which we multiply by the residual, r of x, and we integrate with respect to dx. And the argument we make here is that this is all equal to 0. This is equation 3. We note here as well that we have a subscript I here. This subscript I means that we can have more than one weighting function depending upon the type of problem that we're trying to solve. The specific weighting function that is used will depend upon the method chosen. There are numerous methods available in the literature, but in this course we'll be looking at what's known as the Gallican method. In the Gallican method, we start by defining what we consider to be a suitable approximation for y. After this, we then specify the weighting function to be the same as the approximation function. The best way to explain this is through an example. The example that we're going to use is a simply supported beam, length L, with an end moment applied equally at both ends, which has a magnitude m0. The section properties of this beam are E and I. The governing ODE for this problem is given by EI, which is the factual rigidity, times by the second derivative of y with respect to x, minus a function for the moment, which is dependent upon the position along the beam x, and that's all set equal to 0. Just as a reminder, we can put our coordinate system on the beam, so x runs along the beam, y runs perpendicular to x to denote the vertical displacement. If we go back to equation 2, you'll notice that there are some similarities between the governing differential equation and the residual. We can see that firstly, D is equal to EI and Q is equal to m of x. So we can see then later how we'll work on that and convert that into a residual. I mentioned before that we were going to use an approximation for y. In this case, we've decided to use an approximation function y of x, which is of a sinusoidal form, which has an amplitude a and a function, a continuous function, sine pi of x over L. This is equation 5. This is equation 4. The reason we've chosen the sinusoidal function is because it can be differentiated any number of times, and also the general form of a sine function is similar to that of a displaced beam. When you look at a displaced beam, it tends to have some kind of curvature like this. When you plot a sine function, depending upon where you are in the cycle, it also has a similar profile. This is why we're using this trigonometric function. The value a, this amplitude here, is currently unknown, and the objective of this exercise is to try and find out what the value of a should be. For reference, we note that the exact analytical solution to this problem is given by y of x equal to m0 times by x over 2 ei times by x minus L. This will be left as an exercise to compare the maximum value of this exact analytical solution to the one that we're about to derive. To work through this procedure, we take two primary steps. So step 1, this is to form the residual. In order to form the residual, we need to gather together all the information required to go into equation 2. As a reminder, equation 2 looks like this: d times by d2h of x divided by dx squared plus q, and that's not equal to 0. As was said before, the key assumption of this method, of the method of weighted residuals, is we say that y is equal to h of x. With this in mind, we can then begin to piece together all the bits of information. As shown in the problem, m of x is equal to m naught. Remember as well, we said before that q is equal to m of x, and because the only specified m in this problem are the n moments m naught, and they're constant all the way along the beam, because this is a fixed n moment problem. So we can say that m of x is equal to m naught. Y of x, which is our approximation function, is equal to a sine pi x over L. And now we just differentiate this function twice. So the first derivative is y prime of x, which is equal to pi over L times pi a cosine pi of x over L. And the second derivative is then equal to minus pi over L squared a sine pi of x over L. Putting all this together in equation 2, we end up with a residual that looks like this: minus ei times by a times by pi squared over L squared sine pi x over L minus m naught not equal to 0. And for clarity, we can see that this part here is equal to d. This part here is equal to d2h of x divided by dx squared, and this part here is equal to q, which is equal to m of x. We'll call this equation 7. The second step is then to form the weighted residual integral. The weighting function w of x is the same as the approximation y of x. This is what we said as being a key assumption of the Galerkin method. So in this case, we've only got one weighting function, so we call it w1 x, and that's equal to sine pi of x over L. If you then remember that equation 3 looks like this: it's the integral from 0 to L w1 of x times by the residual, which is also a function of x. Putting the equation that we had in 7 into this, we get the integral from 0 to L, our weighting function sine pi of x over L, then our residual minus ei a pi squared over L squared times by sine pi of x over L minus m0. And that's all integrated with respect to dx. Just for clarity, we can label the components of this integral. This is wx, and this part here is the residual rx. We're now in a position to integrate this, which is easier than solving the differential equation that we first presented. And if we perform the integration of this equation, equation 9, we end up with minus ei pi squared of a over 2l minus 2m0 L over pi, and in this case, as we said in equation 3, this is all set equal to 0. This is the method of weighted residuals that allows us to say this. If we rearrange this equation, we are now in a position to solve for A. So we can say that A, which is the magnitude of the deflection, is equal to minus 4 m0 L squared divided by pi squared EI. Finally, if we want to get the full deflection profile of the beam, we can go back to our approximation function yx, and we substitute in for the value of A. So we said that yx is equal to a times by sine pi x over L, well, this is now equal to minus 4 m0 L squared divided by pi squared EI times by sine pi of x over L. At x equal to L over 2, this function is a maximum, and so we can say that y max is equal to y x is equal to L over 2, and then that's just simply the same as the magnitude, which is equal to minus 4 m0 L squared divided by pi squared EI. As an exercise, you can then compare this deflection that we've calculated here against the analytical solution that we presented earlier by setting x is equal to L over 2.